Okay, it's great to be here, and I hope you can all hear me. I'm going to talk about the national status of accelerated bridge construction, and that, of course, includes Texas, because Texas is part of the nation. So I'm going to start first with an introduction on what we really mean by accelerated bridge construction. Then I'll talk about some of the prefabricated bridge elements and system types that are used for accelerated bridge construction, an overview of all of them, and then I'll go into some case studies with some of the most popular ones currently around the country. Then I will talk about some exciting stuff that Texas is doing for accelerated bridge construction. So a few brief words about resources so that you can get some of this information online and also learn more. Excuse me. Okay, so what are we talking about? What do we really want with accelerated bridge construction? What we really want is replacement or new bridge construction that uses innovative design and construction and high-performance materials to have a cost-effective, long-lasting bridge that was completed with increased safety during construction and reduced traffic disruption in a shortened on-site construction time. That's what we're talking about. Briefly, the definition is just bridge construction that uses innovations to reduce on-site construction time, and the innovations may be in any phase of construction, planning, design, materials, construction. Many ways to innovate, many ways are being used around the country for accelerated bridge construction. It depends on the project. Each project is specific, depending on the site constraints and other constraints. And so it's a great challenge to figure out what's the best way to go with these projects. Some examples of ABC innovations in planning may be early environmental clearance and permitting, and innovative contracting strategies such as A+B bidding or length rentals or incentive-disincentive clauses, etc. In design, of course, it's prefabrication with bridge elements such as modular deck beams and precast substructures, or with entire superstructure installations such as using self-propelled modular transporters or lateral slides. I'll talk a little bit about, show a case study on each of those, and as well as a couple of case studies on elements. Materials, high-performance concrete, that doesn't mean high strength necessarily, because you may not need the strength, but certainly improved durability. And then also high-performance steel, lightweight materials such as lightweight concrete, lightweight backfill. And then construction, using the innovative equipment. Is it self-propelled modular transporters? Is it hydraulic jacks for lateral slides? Is it strand jacks to lift a bridge into place, a whole span into place? And then use of innovative scheduling in the project, such as building substructures prior to the existing bridge being closed, build it underneath. Lots of innovation being done there to speed the project once the bridge is closed. So with accelerated bridge construction, we're really talking about time, reduced time. And so there's definitions related to that. I'm talking about the FHWA's everyday counts definitions. And for on-site construction time, it's when the contractor alters the project site until construction-related activity is removed. And then a subset of that is the mobility impact time. That's when the traffic flow is impacted by construction activities, and that's when the lane closures start, or full closure. So with the impact time, there are different tiers that are being looked at. Hours is tier 1, and there are many projects that are being done in hours. And then tier 2 is like a weekend. And then it goes up to tier 5, which can be greater than 3 months, but much shorter for these large projects that would have been done if accelerated techniques, some type of acceleration wasn't done. So I've talked quite a bit in this about reduced traffic impacts and reduced on-site construction time, because those are the primary drivers for the use of many of the projects that we see nationally with accelerated bridge construction. But there are a number of other reasons that accelerated bridge construction is done. Contractors have asked for field changes to use accelerated construction techniques to improve the work zone safety and to improve site constructability. That's a common factor going around the nation. And then also some do use accelerated processes such as full-depth deck panels, precast full-depth deck panels, because of the improved material quality and product durability. Oregon DOT is doing that. They are not using full-depth deck panels on their bridges because of the the acceleration necessarily, although that's a byproduct. They're doing it for durability because it's a better product. And then minimized environmental impacts if you're working in wetlands, or et cetera. It minimizes the impact to the existing site, and then reduced life cycle cost if you're looking at the full service life of the bridge. So that's a brief introduction. And now I'll talk about what do we mean when we say prefabricated bridge elements and systems for accelerated bridge construction. So PBS, prefabricated bridge element system, PBS, is just one type of ABC. These pieces or systems are built off-site. That could be in a precast plant, in a steel fabrication plant, or it could be adjacent to the alignment by the contractor. And it typically includes features that reduce the on-site construction time and mobility impact time. Elements and systems, we're going to talk about those. So there are deck elements, partial depth precast deck panels. Texas has always been the nation's leader in partial depth deck panels. The use of them, half a decade. I'm going to talk about some really neat stuff that's being done by TxDOT now that takes it to the next level. And then there's full depth precast deck panels. That's very, very popular. Then there's some use of fiber reinforced polymer deck panels, as well as steel grid panels, either open or concrete filled. Then there are prefabricated beam elements. Modular decked beams is a very, very popular one. I'll talk more about it. And then there are a number of different adjacent beams, decked bulb Ts, double Ts, box beams, slab beams. TxDOT has used box beams, slab beams so much that they don't even consider those accelerated, but they do accelerate the project because there's no full forming of the deck, and that eliminates a whole process that's very time consuming. And that's how FHWA currently defines their beam elements. So the modular decked beams, there's a steel beam with concrete decks shown here. The one on the left is it's very interesting. This is just I-beams with 2 I-beams, and before that gets to the bridge site, the deck is cast on it. Very, very popular. Not efficient with the use of steel. So there's some efforts underway to do these newer, more efficient shapes in steel, this folded plate beam, relative newcomer. But the bulk are being done like this because of the simplicity of fabrication and construction. And then the modular deck beams, the concrete beams with concrete deck, this is very interesting. The Northeast Precast Prestressed Concrete Institute has developed, their Northeast Committee has developed this Northeast Extreme T or next beam, and that is just a double T. TxDOT had a double T for many, many years as a standard. When I was working there, we thought it would take the place of box beams. It didn't, and it's been removed because of lack of use, but now the Northeast is really excited about this. I'll show one of the case studies with the use of that beam. And then there's full width beam elements, and that just includes the truss or arch spans without a deck, because the reason they're elements, not systems, is the deck has to be, once they're put in place, the deck has to be cast, so that's that extra construction step, according to FHWA definitions. And then precast and steel segmental would also fit this category. And then there's lots of pier construction, substructure construction, the interior supports of beam construction. And it could be caisson caps, pile caps, either steel or precast, columns and caps, steel or precast, and precast footing. So anything in the interior substructure down to the footings can be prefabricated, and is being prefabricated around the country. The substructures are a relative newcomer relative to the superstructure work with prefabrication. Abutments, same way, anything, precast caps, back walls, wing walls, footings, sheet piling, steel or precast, the full height wall panels, MSE walls, GRS abutments. These are the geosynthetic reinforced soil abutments. There's a picture of one right here, and the local governments really like this because their local forces can actually build that themselves, and it's very economical. So it's good for local bridges that meet the criteria. You have to be concerned about scour issues and others, but FHWA has provided a lot of good guidance on this. Then we have miscellaneous items, precast approach slabs and parapets, and then closure pours and overlays fit into that because durability is a big, huge priority with these. So we want to make sure the closure pours, the closure joints that are done at cast in place in the field to connect these members, and the overlays, if overlays are done well. So prefabricated bridge elements that are currently of most interest nationally are the modular deck beams, the steel and the concrete, and these are just some examples of those, and the 2 case studies will show you more on those. So prefabricated bridge systems, these are systems that can be rolled, launched, slid, lifted, floated, whatever in place, but they're whole systems that are pretty much ready to go. You know, this one even has the signs and the lights and the stripings and everything on it. These are just different examples of some of those that have been done around the country. We have only done in the United States superstructures. Elsewhere in Europe, they've done superstructures with pier and superstructure with the total bridge in these moves. So we're doing a lot, but we haven't done any more than superstructures with these span moves yet. So the prefabricated bridge systems currently of most interest are the superstructure spans that are moved in with self-propelled modular transporters, such as these 2, and superstructure spans that are laterally slid into place with, typically with hydraulic jacks, or there's other methods, but mostly with hydraulic jacks. So that kind of talks about the different types that are being done around the country. Lots and lots of work here. So I'm going to go over in more detail so you understand a little bit better some of these most popular systems. So I'm going to start with Vermont. Now, who would have guessed that Vermont would have an accelerated bridge program that's a priority? I mean, it's a rural, kind of a rural state. You wouldn't think it would, but they do. And this is one project that, and it's got a 3-week closure. 3-week closure, so it's the longest closure of anything I'll be talking about. It's design, bid, build. It's a rural project, rural road. And there were 2 bridges on this project, and here's the road. And we're going to talk a little bit about this bridge construction, bridge number 8. And if you'll see here, this is the detour. This is the closed road, and this is the detour right here. So lots of a fair distance is required for some of these projects in Vermont, and that's why it's a priority to them. They have detour problems detours can be very long, as well as other issues. Limited access. So primary reasons for the use of ABC for this project was to reduce the traffic impacts. Now, they had 7,000 average daily traffic there. Now, you're going to see some lot bigger numbers here, but for them, 7,000 was a lot. Reduced on-site construction time, improved work zone safety, and minimized environmental impact. So as you see, there's usually more than one reason that ABC is used in a project. And look at this. This is a tiny little project, 56 foot long, it's 40 foot wide, single span. So it's not a big project, but it's using accelerated construction. Accelerated bridge construction can be used for any size of project. In cities, in country, it doesn't matter. Typically, these projects have more than one accelerated a prefabricated element or system. In this case, it also has the abutments. It has the abutments, the beams, and the approach slabs, and you can see one of the abutments going into place. It has these next beams. This shows one going into place. It's just a double T. It's got a back wall here. Going into place, it has an 8-inch wide longitudinal joint, so that's not a very wide joint for these superstructure systems. And it had, most of these projects do have other ABC technologies, included full lane closure is becoming more and more popular. Just close the bridge down, do it really quickly. It has incentives, disincentives, lump sum bonus, value engineering, asphalt overlay with membrane on this one. You can see here with how small this is relative, and that's all the concrete that has to be placed. So that really speeds up the on-site construction. 3-week closure. Now that was a design bid build project. This one is a design build project, and it was done in Massachusetts in a city environment. It was done in 2011. It's Salem Street Bridge eastbound, and it's part of the I-93 Fast 14 projects that included 14 bridges with a total of 41 spans done over 10 weekends. Unbelievable. This one is a 60-foot long by 69-foot wide 3-span bridge. It's through the city of Medford. It uses modular deck beams, steel beams in this case, 1 week closure. Primary reasons, again, reduced traffic impacts. Now we saw 7,000 Average daily traffic in Vermont, this is 181,000 here, so quite a bit of difference, and that was absolutely the primary driver for this project. But there were other reasons as well. Improved site constructability is one, and you can see the beam here. It's that steel beam, two beams and deck on top. Many of these projects have to have the abutments and the interior supports repaired prior to excuse me, putting the new superstructure in place. And so a lot of that work is being done while the existing bridge is under traffic. And that's what happened in this case. That requires a lot of ingenuity. It's specific to the project. You can see there's 6 modular deck steel beams per span here. They're being placed here. This one is different. Now, this one has, you can see that it's quite a bit larger closure join here. This is 32 inches as opposed to that 8 inches before, so that's a lot of concrete to place. The reason that was the case for this project is they were optimizing their crane side versus what they needed on the site for other reasons versus, the pick weights of the beams relative to the other components on the site. So it takes a lot of coordination with all the specialties involved. It also had a link slab, what's called a link slab over the interior support rather than the simple for dead, continuous for live. It had a number of ABC in addition to the prefab. Massachusetts has its own decision-making process that it uses. That's happening in a lot of the states now. They're developing their own decision-making process to determine whether it's ABC or conventional construction works best, early environmental clearance, electronic submittals and approvals, and then the various other ones that we've mentioned before. So this project, the I-93 southbound was detoured Friday at 8 p.m. and it was fully reopened Monday at 5 a.m. That's unbelievable for that kind of work. Very short closure times and impact to traffic. That was elements. That was elements, putting the pieces together, but bigger pieces. And this is systems. This is a systems case study. This is the one on the rolling in with SPMTs, self-propelled modular transporters. This was a relatively small job. It was in the town of Wellesley in Massachusetts. 530 tons, self-weight's not very big. We have some that are quite a bit heavy, much, much heavier than that. The design build project, again, in an urban location, a weekend closure. So 39,000 ADT in this case. What you'll see is this is a tiny little bridge. It's 42-foot spans, but it warranted the use of self-propelled modular transporters because of the impact to traffic. For this location, that was their priority, as well as some others. You can see there's lots of reasons to use it, but the primary one was the impact to traffic. They had a number of precast elements, abutment caps and pier caps. They had to take down the abutment caps and pier caps because they were deteriorated once they removed the old one and put new caps on. And then they do a lot of precast approach slabs being done now, as well as the system, superstructure system. Now the reason contractors, many of them like these system moves is because they can build these projects can be built on site. It's not in the final location, but it's close to the final location, and it's conventional construction. So it's not that different. They just need to figure out how to most efficiently move it to minimize traffic disruption. So in this case, this is in the city of Wellesley. So here's the bridge. They demolished the old bridge. They're working on it, and then they repaired the existing substructure, installed the precast caps, and then here now they've started the move of the 2 spans with these SPMTs. And then that's the bridge in place. So it was closed Friday at 10 p.m. and reopened Monday at noon. And this happened to be July 4th. That was, depending on the location and what the traffic patterns are, you determine when it works best for the closure. And then the second case study, a systems case study, is with the lateral slide. And this one is not a new project. It was done a half a dozen or so years ago. And it was done in Oregon. And it's a 2-span superstructure lateral slide. Here's the new bridge. It was a design build project. And they're done design bid build, design build. CMGC, all sorts of different methods being done with these. This is a tunnel, so they couldn't detour the traffic, so they needed to do it really quickly. So it was a weekend closure of Oregon 38 in a rural environment. Primary reasons, I mean, you look at these, I mean, less than 4,000 average daily traffic, but a very long detour. So they were concerned about that. And then, of course, the other reasons to use it as well. Again, conventional construction of the bridge, pretty much conventional. And then, in this case, again, cast-in-place substructure was constructed to the extent it could be underneath the bridge before it was closed. And then if it had precast multi beams and then wing walls one side. Okay, so what happened is they built this bridge along this side, and here's where the alignment is, and they just moved the bridge over. This shows it after it was moved over. So they could build this, they could cast in place this wing wall on this side, but they couldn't on this side because the bridge was in the way, so they just precast one of the wing walls because that was the easiest solution to get it to minimize traffic disruption. And then it has approach slabs and sleeper slabs. Here are the approach slabs that'll be put in, and the sleeper slab is just the support on the other side of the bridge. So again, Oregon also has its own state decision-making process used in early environmental clearance and permitting and some of the others that we talked about before. So closed on a Friday at 8 p.m., reopened Monday at 5 a.m. Unbelievable. This work is just unbelievable that's being done these days. Okay, so that's kind of a look at some of these case studies, and then we'll be talking about the ABC in Texas. As I said, for half a century, Texas has been the leader with partial depth precast deck panels. As you can see with these panels, they have a lot of, still had a lot of form work to be done in at the ends of the regions, at the supports, and also on the overhangs. And so TxDOT is remaining a leader, and now they have developed a second generation precast overhang panel. You can see the detail here. Here's a full depth overhang panel. It has the steel running through it into the first bay, full depth, and then it can continue with the partial depth panels. What I like about this is they've done all the work now with this, and so they could just continue the full depth all the way across too. So they have lots of options now, and most of the work has been done. It's not a standard yet, but John Holt said that it was. They're looking at doing the standard now. It's been constructed in a bridge. Several bridges, I guess. Here's the layout. Looking down, it just shows that here's the overhang, and here's the first bay, and then here's the support, and you can see there's much, much less, this is I'll show you the next slide, which shows kind of the detail of this, and so it's a lower portion here where you have the concrete poured. Just a very efficient section for the end overhang panel, and then similar for the interior overhang panel. TxDOT has also done a full depth deck panel bridge, and this was done back in 2008, and it was with the latest research that had been done by NCHRP, not requiring post-tensioning or an overlay. The issue here was that the closest batch plant for cast-in-place concrete was 75 miles away, and that makes for a tough time trying to get good concrete. And bent caps. Texas has been leading the nation with precast bent caps also. This one is a late 1990s project that through Houston, they had prefabricated bent caps, saved lots and lots of money. They had both steel and precast. Then in early 2000s, these are some very well-known bridges, the Lake Ray Hubbard and the Lake Belton. And the Lake Ray Hubbard, the contractor requested the precast caps to reduce work near power lines over water. And I don't know if Bill DeGay's here. He was the contractor. Is Bill DeGay here? I think he was going to be. Yeah, there he is. So he's been an innovator with ABC for many, many years, and he started TxDOT, working with TxDOT on these precast bent caps. These are all reinforced concrete. Precast reinforced concrete bent caps. They've had for a number of years now these options on the website, but now again innovating. They are pre-tensioning these. They've been built on a project, and these are to address any issues that may be occurring with cracking. And it's been done on a project in San Antonio, and you can see how these can be very efficient. I mean, when you have repetitive construction, that becomes certainly a cost-effective and efficient means of getting those caps in place. Also, superstructures in Houston, the US 59 Gateway Tied Arches, that was done back in the mid-90s, very efficient superstructure that was done to minimize traffic disruption and maximize vertical clearance. And then in 2007, the Loop 340 bridges near Waco, where it was a full, these precast, pre-topped U-beams that were placed on the side of the project and completed, and then quickly moved into place with minimized impact to I-35 traffic. Very attractive. It also had precast column shells as well. And now you're doing your first lateral slide. It's going to be presented tomorrow. How exciting. Just continuing being on the cutting edge of this ABC work. The Bridge Division also has a proposed ABC policy. You saw I said decision-making policy is the states are developing their own, and that's also going on in Texas now, where they're asking the districts if they want to investigate ABC for a project, and then if so, they'll do that decision-making to make sure it's a good choice, and then they're developing tools and for assistance, and we'll need some input from the district to accomplish that. Resources, FHWA, you can just go FHWA ABC, Google, and you'll get the website with a lot of information. Every Day Counts is a website that's a current initiative. Every Day Counts 3, it's EDC 3. There's some live broadcast of some of the presentations now. You can just listen to them from your office. This one is on the ultra-high performance concrete connections. That's to not have a problem with durability of these connection details for the closure pours. You can see the times. You can go to this website. You can just Google Every Day Counts and get these. There's also one on the geosynthetic reinforced soil integrated bridge system. And then others too. These are a few of them that also improve accelerated bridge construction for the various projects. You can look through those if you go to that site. The ABC University Transportation Center is shown at this, has a website here. I'm affiliated with them. We do monthly, free monthly webinars. The next one is this Thursday on accelerated bridge construction in Pennsylvania. There's an in-depth web training coming up on the 4th that has to do with that I-93 Fast 14 project I talked about. There's an ABC conference in Miami with pre-conference workshops. Registration deadline coming up for that. And that's my presentation. Thank you very much.